Section 4.1, translations. So chapter 4 is very kind of artistic in what we're learning. It feels maybe a little less math-like and more art. So the first vocab word is a vector, and it is a quantity with direction and size. It's represented by an arrow. It has the initial point and the terminal point. So it can be a long arrow or a short arrow. It can go in whatever direction. That's a vector. Oftentimes used in science also. So the component form of a vector is a way to describe the vector without having to draw it. So if you have maybe a picture like this, you have a vector like this. The component form, it's two numbers. The first number represents how far left or right the arrow goes. So this arrow goes 2 units to the right and 1 unit up. So the component form of that vector is 2, 1. This particular definition is backwards. The first value is the x value, the second value is the y. It's the change in the x and the change in the y. If one of these were negative, it would just mean it was going left or it was going down. A transformation is a function that moves or changes a figure basically by doing something to it. You guys probably have seen Transformers, or possibly have seen Transformers where cars and vehicles and stuff turn into robots. And every time Bumblebee changes from a car to a robot, the change occurs the same way. He's transforming. So maybe a transformation takes this A and turns it into this A. Now one of these is called the image and one of them is called the pre-image. And for me, this is, for whatever reason, tricky because I always say image and pre-image. But think about what pre means. Pre means before. So the pre-image comes first. This is the pre-image, is the little one, and the big picture is the image. And we typically say if this is point A, let's see here, maybe let's call it point R. This point would be R prime. It gets a little apostrophe type mark after it, R prime. Optimus Prime, I don't think that's a coincidence for his name. All right, a translation. A translation is a transformation where essentially your picture slides in one direction. So maybe this box here slides there. Everything slides down and to the right. And we call this rigid because the picture doesn't change. All of the transformations we're doing in 4.1, 4.2, 4.3 should be rigid transformations. That means it doesn't change shape or size. So this is a translation. And let's say this translation went 2 right and 3 down. Went 2 units to the right and 3 units down. Well, we would say that it was translated by the vector 2, -3. We could also, though, say that every x and every y was changed by adding 2 to the x and subtracting 3 from the y. These two notations are the same notation. This is just the vector form, and this is using the rule. Now, a composition of transformations. A composition is when you are taking multiple things and putting it together, like composing music, taking lots of notes and putting them together to make one thing. So here, maybe you take your square and you move it down here. But then we take that square and we move it up here. This is a composition, because instead of going from step 1 to step 2 to step 3, we could have essentially skipped the middleman and gone straight from the beginning to the end. It's multiple transformations put together. A postulate, a translation, is a rigid motion. If you take your shape and you slide it over, it doesn't change. That's called rigid. Now, the composition theorem, the composite of two or more rigid motions is rigid. So if you take a shape, maybe you take the pen, you slide it down, and then you slide it to the right. What this says is that the pen has not changed shape, the pen has not changed size. Each time you move it, up, down, left, right, whatever direction you move it, it doesn't change. That's the composition theorem. Let's do a couple of these and see how they work. So example 1, the vertices of triangle ABC are A, 1, 2, B, 5, 1, C, 5, 4. Translate triangle ABC using the given vector, and then graph ABC. So what I want you to do is when you do these problems, I want you to write down A, B, and C. So A is 1, 2, B is 5, 1, C is 5, 4. We're going to make a little T-chart here. Now, when A changes, when A is moved, it turns into A prime. B turns into B prime. C turns into C prime. This vector here, negative 4, 0, that means we're going to subtract 4 from the x. I'm going to do x minus 4. And for the y value, you add or subtract 0, which does nothing. So subtract 4 from the x and leave the y the same. So 1 minus 4, 5 minus 4, 5 minus 4. And the y values are going to stay the same. 2, 1, and 4. A prime. 1 minus 4 is negative 3, 2. B prime, 5 minus 4, 1, 1. C prime will be 1, 4. Now they want us to graph. So notice this particular graph is counting by twos. So 1, 2, up, or right 1, up 2, 5, 1, right 5, up 1, 5, 4, up here. A, B, C. And it's necessary for you to label ABC. And then notice this is triangle ABC, so we should actually have a triangle. Now we're moving it. A prime is negative 3, 2. Negative 3, 2. B prime is 1, 1. Labeling A prime, B prime, C prime. C prime is 1, 4. And you connect your dots. Make the triangle A prime, B prime, C prime. Let's try example B. A is 1, 2. B is 5, 1. C is 5, 4. A, B, C turn into A prime, B prime, C prime. Here the rule, the vector is 1, negative 3. That means we're going to take x and we're going to add 1 to it. And we're going to take y and subtract 3. That's going to be what we do. So, the x value is 1, add 1. 1 plus 1. Take the y value, subtract 3. And our A prime is 2, negative 1. Do the same thing with B. Take the x, add 1. 5 plus 1. Take the y, subtract 3. 1 minus 3. B prime is 6, negative 2. C prime, take the x and add 1. 5 plus 1. Take the y, subtract 3. 4 minus 3. C prime is 6, 1. I want you to show this work. I want you to organize it in a way that I can follow. The chart, although it's not the only way to do it, is a really good way to organize your work. And I need to see you adding 1 and subtracting 3 because I need to know that you, if you're getting the wrong answer, I need to know that you're doing the correct process. So let's graph. A, B, and C are still the same 3 points. A, B, C. Just copying it from part A. Now A prime is 2, negative 1. B prime is 6, negative 2. And C prime is 6, 1. Now it's also possible, depending on the scenario, for you to just count. This vector here means you go right 1 and down 3. So you could actually, for each point, count right 1 and down 3. Right 1, down 3. Right 1, down 3, and get your new points. You don't have to go through the whole chart, but the whole chart kind of is like buying some insurance in case you count wrong or something like that. Example 2, write the rule for the translation of quadrilateral PQRS to quadrilateral P prime, Q prime, R prime, S prime. So let's see here, we have 2 rectangles here, and we either go from the left to the right or the right to the left. And in my opinion, this is probably the hardest part to figure out. So, which one is first? Which one are we starting at? The solid or the dashed? Do we start at P or P prime? Look, your chart went from A to A prime. We start at the one without the prime. So we're starting at P and we're going to P prime. So from P to P prime, how far left or right did we go? And you count. We went 1, 2, 3, 4. 4 right. How far up or down did we go? 1, 2, 3, up 3. So in vector form, it would be 4, 3. But the rule is the one that looks like this. So what do we do to the x values if we go right? 4. We take the x and we add 4. What do we do to the y values to make it go up 3? We add 3 to those. this is the rule. For example, B. Let's see here. Which one goes first, P or P prime? P goes first, and then it goes to P prime. And I understand back here, I only did P. I didn't even talk about Q, R, or S. But remember, the rule that happens to one of them happens to all four of them. So we could have done Q to Q prime, R to R prime, or S to S prime. They should all have the same rule. So pick whichever one you think is easiest to count. So let's see here. P to P prime, we go right 1 and down, count how far down we went. 1, 2, 3. So the vector is 1, negative 3. The rule, x plus 1, y minus 3. Example 3, use the translation xy arrow x plus 6, y minus 3. What is the image of J? What is the image of R prime? So we're going to use this translation on A and B. And we're going to use it just like up here. The difference is that up here we also had to deal with a graph, and they gave us the rule as a vector. Here they actually give us the rule as the rule. So let's see here. J is the point 4, 5. And we want to use the rule x plus 6 and y minus 3. J, after it is moved, is J prime. Take the x and add 6. So 4 plus 6. Take the y and subtract 3. 5 minus 3. So J prime is 10, 2. What is the image of R prime being 0, negative 5? So notice the words are the same. What is the image of? What is the image of? The only difference is that here they're telling you to start at R prime. We are still using the same rule. The catch is that R prime, it doesn't usually take very many guesses to guess what that's called when we do it again. It's called R double prime. And we use the rule. X plus 6, 0 plus 6, y minus 3, negative 5 minus 3. R double prime is 6, negative 8. Now, if for some reason they give you a composition, 2 translations, you move it and then you move it again. It's not bad. What you do is you move it just like this. Then these become your new starting points and you do the second rule. Sometimes I like to actually make kind of 3-column chart. Maybe I put A is the point 1, 2, and then I do my first rule, which is x minus 1, y. You would get A prime, and then you would do your second rule, x plus 5, y minus 2. I'm making this part up. And you would do A double prime. So you can make your chart bigger and just keep adding to the right, or you can make a complete separate new chart. Either way is just fine. But with this, you should have enough information to do section 4.1 homework.